Hello students, as we were discussing real and math solution, today is the part third of the same lecture series, and in this also we are going to discuss some of the questions that have come in the part B, that is the multiple select questions, and they were a little bit confusing. But regards this paper, I would suggest that just do this paper time and again, because this has set the standards of JAM examinations and other MS examinations. So you will get to know many things from this particular paper, and where to give a halt or where not to give a halt while studying, you will understand. Because in this particular paper, you find questions from each of the domain, except from the applied mathematics was almost out, like it used to be in earlier times. Otherwise, if you see with perspective of pure analysis, this is a very perfect paper, and I will also recommend that those who are preparing for CS and NET should also go through this particular paper, because in that case you will be able to understand each of these small concepts, and these have been asked very beautifully in this particular paper. So let us start. So this is question 57 that has come in here, examination, and this is an easy question. So again, question number 57, limit n tends to infinite, integral 0 to 1 e to the power x square sin nx dx, and this particular question was asked in your examination. So what is the concept involved? So concept that has been involved is Riemann integral and generating inequalities from Riemann integration. So first, let us assume I'll develop a simple question and develop a simple proof for you, and accordingly you can see what shall be the answer to this particular problem. Consider a function f defined from closed interval a comma b to r such that f is continuously differentiable, so that f is continuously differentiable, by which I mean that your function is continuous and the derivative of function is also continuous. So function is continuously differentiable, then limit n tends to infinity integral 0 to say a to b f of x f of x into sine of nx will always be equal to 0. So all in all, you have to see your f of x must be continuously differentiable. Now, clearly from this particular thing, e to the power x square is infinitely differential function. So this is an infinitely differential function. That itself implies e to the power x square is continuously differentiable. Is continuously differentiable for all x belongs to 0, 1. So therefore your required integral, and writing it as I, so your required integral will come out to be 0. Okay, so the answer to this particular problem will be 0. Now you might be wondering what is this? So let us do this particular thing. Okay, so the integral will be 0, and I'm just explaining you as to why it should be 0. Okay, so if I'm supposed to find integral f of x into sine of nx into dx, so let us take the modulus of it. So it will be equal to modulus of, and we just keep fx non-integrable function, we just integrate sine of nx. So sine of nx by integrating will give you minus cos of nx, and integrating from a to b, what you will find? You find f of a cos na, because of negative error, so therefore writing minus f of b cos of nb plus I think integral derivative of this minus, sorry, here we get a minus. So here we get a minus here, but then sine of nx while integrating we will get a plus. So I'll write 1 upon n into sine of nx. Okay, so what you are getting, just see to it. What you are getting, integration a to b f of x sin x modulus dx, you will get 1 upon n modulus of f of a cos of n of a minus f of b cos of n of b, the modulus plus 1 upon a modulus of integration f dash x sine nx dx. Now see, a function fx is continuously differentiable since f of x is continuously differentiable. Which implies f dash x is continuous on a comma b. Since f dash x is continuous, it implies f dash x will attain bounds, that is between in the interval a comma b, f dash x will attain maxima as well as minima, and obviously f and fp will be certainly some values. So what I can do, I can say I can write this 1 upon n fa the modulus plus, I can write this will be greater than or equals to fa modulus. This I think you should be able to clearly understand, because see, cos of n a modulus will be less than or equal to 1, cos of n b modulus is less than or equal to 1, so you are getting fa and fb plus 1 upon n, and here we get integral modulus of f dash x into sine nx dx. Now, what you are getting next? See, so you have it required integral modulus is less than equal to. See, I can write it as 1 upon n less than supremum x belongs to a comma b f of x. So obviously, this will be less than equal to supremum of fx x belongs to a comma b plus, now here you have 1 upon n and you have integral sine x here, so you have f dash x here. So from where to where, from integrating from a to b, so what you find, sine x modulus is less than equal to 1 and f dash x modulus can be replaced by, so I can, since it is less than equal to 0, so I can replace this by supremum of f dash x belongs to a comma b. So sin x is less than equal to 1, f dash x modulus will be less than equal to supremum of f dash x for all x belongs to a comma b, and this will be integral and this will be b minus n. Okay, so effectively I can write your integral mod is less than equal to 1 upon n, so x belongs to a comma b fx modulus plus b minus a upon n modulus of supremum x belongs to a comma b. Now why I am writing this particular thing, you can understand that f dash x is continuous, so therefore it will attain its bounds, therefore it will attain maxima as well as minimum. Okay, no worries. So I believe as n tends to infinity, this will tend towards 0. So you have required integral as n tends to infinity, I will go towards 0. Since modulus quantity cannot be less than 0, it has to be then equal to 0. So that implies the required integral will be equals to 0. So whenever you are supplied with a continuously differential function, whenever you are supplied with a continuously differential function fx, it is multiplied with sin x, and you are supposed to integrate it over a to b, and if you find limit n tends to infinity, the answer will come out to be equal to 0. Please do remember this particular theorem. So accordingly, your answer should be equal to 0. Now next, let us move to another problem that was asked in the examination itself, and this is a very important problem. This was question number 35. So this was question number 35. Again, an easy problem, not an easy problem, but certainly it was covered in our classroom program. So easy question. Let me just write the question. Okay. So the question was asked regarding function's derivative, and it's increasing, and whether it is increasing or decreasing. And this was kind of question that was asked in examination. Excuse me. Okay, so let us take another question first, then we shall take that particular question. Just give me a minute. Just give me. So let us. So the question was asked regarding the derivative and the derivative being greater than 0, and there were options regarding increasing and decreasing. Just let me find the question. We shall begin. So, but in the meantime, let me do another question for you. So there was a question regarding series. So let us do that first. There was a question regarding series. I'll mark the question number also. Just give me a minute. In that case. Okay. So question that was asked was regarding summation 1 upon n की power 1 upon 1 plus n. What can be said about this particular series? What can be said about this particular series? So this was question. I'll tell you the question, but don't worry about it. But just by the meantime, I'm just doing this particular problem. Okay. So summation n raised to power 1 upon 1 plus n. So what happened if an and bn are given to be greater than 0, and if limit n tends to infinity, an upon bn is a non-zero is equals to L, and L is a non-zero limit, and if n is a non-zero limit, then summation an and summation bn behave alike. This is a theorem. This is sometimes called as limit comparative test. So what are you supposed to do? You are just supposed to compare this particular function by 1 over n. So let this be compared with 1 by n, and we have to find limit n tends to infinity, and we will get 1 upon n की power 1 upon n, and this is your homework. Just find this particular limit. You find that limit n tends to infinity, n की power 1 upon n comes out to be equal to 1. So therefore this comes out to be equal to 1, and this is certainly non-zero. And since summation 1 upon n is divergent, it implies summation n raised to power 1 upon 1 plus n is also divergent. So this is also divergent. I hope this was an easy question. Now, regards other option, so summation 1 upon n की power 2 minus n की power 1 upon n. This was asked in the examination. So let us first consider. So I'm writing it as summation 1 upon n की power t. So I'm considering this function. So consider f defined from 0 comma infinity. I think I should exclude 0 to 0 comma infinity, and let function fx be defined as x raised to power 1 over x. Okay, so x raised to power 1 over x we are taking. So how to just know what will be the range of this particular thing, so that I can use this particular thing effectively here. So x raised to power 1 upon x. So what will be the limit x tends to 0 plus limit x tends to 0 plus f of x will be equals to limit x tends to 0 h raised to power 1 over h. So let me say that this is equals to a. So limit h tends to 0 h raised to power 1 upon h. So you take log both sides, log of a equals to limit h tends to 0 1 upon h log of h, and as h tends to 0, this particular I believe this is right. So 1 over h comes this way, log of h goes that way. So 1 upon h and log of h. So as x tends to 0, this particular thing goes towards minus infinity, and as h tends to 0, this entire thing will go towards infinity. So this is towards negative infinity, and this is towards positive infinity. So in totality, this will go towards a very large negative value. That implies a is supposed to be equal to 0. So close to 0, this limit will be equals to 0. So in the right hand neighborhood of 0, we'll get this function's limit as 0. That is okay. Now, as x tends to infinity, as we've already known, same approach, we just take x raised to power 1 over x, will go towards 1. What about maximum and minimum? For that, we'll have to differentiate it. So let y is equal to x raised to power 1 over x, take log y will come out to 1 upon x into log of x. Now this will be 1 upon y dy by dx is equal to 1 upon x square minus 1 upon x square log of x. So when it will be greater than 0 and when it will be less than 0, let us find And since function is differentiable throughout, let me find where function is increasing and where function is decreasing. So if y is an increasing function, then the derivative must be greater than 0. That implies it is an increasing function whenever 1 minus log of x is greater than 0. That is whenever log of x is less than 1. That is whenever x is less than e. So for all x greater than e, I can state that function is your function is whenever x is less than e, whenever x is less than e, the function is supposed to be increasing, and whenever x is less than b, it is supposed to be decreasing. Now, in this particular case, since you have no roots, so I can clearly see that x equal to e is a point of extremum. Okay, point of extremum, and it will be positive side only because y will be equals to e raised to the power 1 over e. This is on the positive side. So an idea to this particular thing can be that this is your 1, this is y equal to 1, and this is your e. So function is increasing. At e, it is attaining a maximum, and then all of a sudden it is decreasing and tending towards 1. So what you can see that beyond this particular point, so let's say whatever this particular point be, say x. So take a natural number n to be equal n naught such that it is equal to greatest integer plus 1. So I'm taking on the safer side n naught is equals to greatest integer x plus 1. That will give me the next integer to this particular x. So if I see for all n greater than equals to n naught, I can clearly state that my function x raised to power 1 upon x will be less than 1. In terms of natural number, if I just use the same for all n greater than equal to n naught, n to power 1 over n will be less than 1. That implies minus n to power 1 over n will be greater than 1 minus 1, and 2 minus n to power 1 upon n will be greater than 1. So, we just write this particular thing so that you will be able to understand. Just write this particular thing so that you will be able to understand the argument. Not less than 1, greater than 1. Okay. Now for all n naught, x to power 1 upon x will be greater than 1. In the limiting In the limiting case, it is tending towards 1, otherwise it is greater than 1. So for all n greater than equal to n naught, so this is your x, I'm just taking a next integer. Why I'm taking next positive integer? Because I'm supposed to do this particular thing for a sequence. Okay? So for all n greater than equal to n naught, n to power 1 over n is greater than 1. That implies minus n to power 1 is less than minus 1. That implies 2 minus n to power 1 over n is less than 1. Okay, that implies your p is less than 1. Okay, what does it imply? It implies that summation n equals to n naught level to infinity 1 upon n to power p and p less than 1. So this particular series of yours, that is 2 minus n 1 upon n to power 2 minus 1 upon n to power 1 over n, I have written as summation 1 upon n to power p. And what I found that your p is less than 1 for some n equals to n naught. So some finite terms can be removed from the series, and what we find that after omission of some finite terms, we are getting this particular series to be diverging towards plus infinity. Therefore, answer should be both of these series must diverge. So answer should be both of the series must diverge. I believe this can be done. I think this was your question that has come in the examination. Let me see the question number so that I'll mark that question number so that you can be able to get the answer. Just give me a minute. So this was your question number. Question number 30. Question number 30. Answer is B. Question number 30. Answer is B. Okay. So question number 30. This was question number 30. The answer is both of these series diverge. Okay. So question number 30. You can see this particular thing here. IISc. So this is question number 13 here. I see this question. First was fairly easy. This is a routine book question. The second was also fairly easy because I think. Let's see how many people have done it. So both of the series must diverge. This is the answer. Okay. Now, regards another question that has been asked in the examination, and this is a very good question, very good question. And you should know this particular question because this is certainly a mistake that we at times do. So what is being asked? See, question as a whole is if f dash. So this is a theorem itself, so no big deal in it. But the second point, so question number 35 regards increasing and decreasing. So question is about increasing function theorem. ठीक है सो हमेशा ध्यान रखना मैथ्स में ये कन्वर्स नॉट ट्रू इन सब चीजों का बहुत ढंग से पढ़ना है जरूरी है हम क्या करते हैं जल्दी जल्दी ये चीजें पढ़ लेते हैं देन वी गेट ऑल ऑफ सडन कंफ्यूजन सो इफ f is differentiable so this is what theorem states if f is differentiable on an open interval then f is increasing if and only if f dash x is greater than equal to 0 for all x belongs to I. So I am including 0 equal to 0 also. So not in the stricter case. In general, I will write that f is increasing if and only if f dash x is greater than equal to 0 for all x belongs to I. Further, I can also state, so this is your theorem. So further, I can also state that if your f dash x is greater than 0 for all x belongs to I, then f is increasing on I. So in general, note that if f is differentiable on an open interval, then f is increasing if and only if f dash x is greater than equal to 0. Further, I can also write that if f dash x is greater than 0 for all x belongs to I, then f is increasing on I. Note that this converse statement is not true. So converse of the above statement is not true. Converse of the above statement is not true. So why it is not true? Because in examination, the converse of the above statement is not true in the sense, see, that is if f is increasing on I, if f is increasing on I, on your given interval say a comma b, it not necessarily implies that your f dash x will be greater than 0 in a comma b. Why? It might be possible that it may be 0 at some points. So if f is increasing on a comma b, does not necessarily imply that f dash x will be greater than 0 in a comma b. Let us see how to do this particular. So let's see. Okay, so converse of the above statement is not true. So if f dash x is greater than 0, then f is increasing on I, and if f is increasing on I, it does not necessarily imply that f dash x is greater than 0. It might be possible that it is 0 at some points. Okay, so how to go about this? So for this, consider this counter example. Consider this counter example that I am giving to you, and you have to remember it always because these type of questions might be asked in your GATE, NET, otherwise question examination. So I am giving you an example: 2 minus cos of log of x minus sine of log of x whenever x belongs to 0, 1, and whenever x is equal to 0, let me extend it to 0. Okay. Now this particular function, as you can clearly see, if I just see the f dash x is given over so f dash x will be equals to what? So let me evaluate f dash x. So what will you get? F dash x is equals to 0 if x is equal to 0. And what about if x is not equal to 0? So what about x is not equal to 0? If x is not equal to 0, then you can simply differentiate it. So you get 2 minus cos of ln x minus sine of ln x. And then x and this thing you can multiply, so you get plus cos ln x के derivative you get sine minus sine So sine of ln x, and then ln x you can get 1 over x, so you will get cancelled. And this will be cos of ln x, and again ln x the derivative 1 over x, and you get cancelled. So this will get cancelled. I believe, oh sorry, I made a mistake somewhere. Okay, so here it will be negative. So this will remain there. This will remain cos of ln x, and so this will get cancelled. So f dash x has come out to be 2 minus cos of ln x. Now, so for all x belongs to 0, 1, for all x belongs to 0, 1, ln x will lie between minus infinity to towards 2, 0. And if these are the values, I can clearly state your cos function will lie between plus 1 to minus 1, and that itself implies that your f dash x will be greater than 0. But f dash x might be 0 as well. So यही क्वेश्चन में नहीं दे रखा था, might be 0 as well. So कहाँ 0 हो जाएगा? So clearly as x tends to 0, cos of ln x will tend towards minus infinity. So cos of ln x will oscillate between minus 1 and 1. So in order to know this particular thing, what you can do, you can simply write, since cos is an even function, so I can see what I am supposed to do. I'm supposed to find that what all will be the points where 2 minus 2 log cos of log x is 0. So it will be 0 only when cos of log x is 1. So I'll simply replace it by cos of minus ln x. There is a trick why I'm doing it, because if I use this, then I will not be able to appropriately tell you this. But in this particular case, I will be appropriately able to tell you in this particular interval at what output. Because cos is an even function, I don't think there will be an issue with this. So I think this will be equals to 2n plus 1 pi by 2. So your minus ln x will be this. So your x will be e to the power minus 2n plus 1 pi by 2. That implies your x naughts, where f dash x naught is 0, will be 1 upon e to the power 2n plus 1 pi by 2. Since its limit point will be 0, so that implies there exist infinitely many x naughts, x naught belongs to 0, 1, such that f dash x naught is equals to 0. So your function is increasing. So this particular function is increasing, but it does not necessarily say this particular function is increasing over closed interval 0, 1. But it is not necessary that f dash x is greater than 0 in a, b. In this particular case, as you can clearly see, there are infinitely many points where f dash x is equals to 0. So according to the question that has been asked, as if dash x is greater than 0 in a, b, implies f is increasing in a, b. True. If if f dash x is greater than 0 in open interval a, b, then f is increasing. We just give it. I think this was a question number 35. So I believe question number 35, the answer should be A and C, because if f dash is greater than 0, implies that f is increasing a, b. Yes, true. This is the theorem itself. And if f is increasing a, b, implies f dash x is greater than 0. F dash x is greater than 0. Obviously, this serves as a counter example because it is not necessarily true. There are infinitely many points where f dash x is equals to 0. So your option number B is rejected. So option number A is true. So I believe this is true by the theorem itself. So that I have stated already initially, that you can see in your real analysis textbooks, no big deal. But this particular counter example, you must remember, even in your interviews, this will be a great reference. Now regards to other options, one given that your f dash x naught is greater than 0 for some x naught belongs to a, b, then there exists a del such that fx is greater than fx naught for all x belongs to x naught, x naught plus del. Now by the definition of differentiability itself, so by differentiability, the definition of differentiability, what do you get? You get f dash x naught is equal to f of x naught plus del minus f of x naught divided by del. Say that x belongs to x naught comma x naught plus del. Okay, so if I simply write f dash x naught is greater than 0, it itself implies that f of x naught plus del. So I'll write this here. Okay, if f dash x naught is greater than 0, it itself implies f of x naught plus del will be greater than f of x naught. What does it imply? It implies there exists a neighborhood del such that f of x is greater than f of x naught, where x belongs to x naught comma x naught plus del. This follows from the differentiability itself. So this follows from the differentiability definition of differentiability, and if I'm saying this, so I can also write that here f dash x naught is equal to f of x naught minus del comma minus del minus f of x naught divided by minus del. So if I'm writing this is greater than 0, it implies f of x naught will be less than f of x naught minus, sorry, in that particular case greater than 0. So I'm sorry, this will be less than 0 in that particular case. So this will be less than 0. It implies f of x naught will be greater than this. It implies that exists a neighborhood so that f of x f of x is less than f of x naught. Okay. So see again by the differentiability itself. So f dash x naught is equal to f of x naught plus del minus f of x naught. Now see, this is your del. So in your neighborhood, say in your neighborhood. So now you can vary this del, right? You can vary this del. So I can clearly see that x, it varies from x naught, so x naught plus del. I can clearly state that this particular point will be greater than 0, since I've already stated that f dash x naught is greater than 0, since del is greater than 0. So in general, what I can do, in general, I can write this particular fact as sum below. Okay, so f of x will be greater than f of x naught. So option number C must be true by the definition of the differentiability itself. So by the definition of the differentiability, see f dash x naught is greater than 0, it implies f of x naught minus del minus f of x naught will be less than 0, which implies f of x naught will be greater than, see this is this particular thing, I can write f of x naught minus del must be less than 0, which implies f of x naught must be greater than f of x naught minus del. So where you're going towards, now since del is arbitrary, so what I can do in this particular neighborhood, I can write this particular thing to be x. So clearly f of x will be less than f of x naught for all x belongs to x naught minus del comma x naught. And for all x belongs to x naught comma x naught plus del, I can write that fx will be greater than f of x naught by the definition of differentiability. Okay, so by the mere definition of differentiability, option number C will be true, and for option number D, it is this classic complex example that can serve to reject this particular thing, that whenever your f dash x is greater than 0, whenever your f dash x naught is greater than 0, it does not necessarily imply f is increasing in some neighborhood of very standard counter example. So this is something that we can already in our classes. So f dash f is increasing in the neighborhood of, so it does not necessarily imply that f is increasing in the neighborhood. So example के तौर पर लिख लीजिए f is equal to x plus x square. I can sign of, I believe that I can write 1 over x also and 1 over x square also, x not equal to 0, and whenever x is equal to 0 you can write it as x equal to 0. See, so f is differentiable everywhere, like x equal to 0 you can find, x equal to 0, 0 is a constant, x not equal to 0, this is a differential function. What about differentiability at x equal to 0? We simply find f dash 0. So what will be f dash 0? So f dash 0 will be equals to limit x tends to 0, f of h minus 0, f of 0 divided by h. So what do you get? And simply get h plus h square sine of 1 over h square minus 0 divided by h. So what you get? We get 1 from this. You just take h common out. So h square into sine of 1 over h square, as h, you will simply see that this is h into sine of 1 over h square. So this will converge towards 0, and this will converge towards 1. Obviously, so f dash 0 comes out to be equal to 1, and certainly it is greater than 0. Now, does it imply f is increasing in the interval 0, 1, increasing in interval 0, 1, answer is no. Yeah, 0, del, answer is no. Why? See, let me find f dash x for you. So f dash x will be equals to 1 plus 2x into sine. This you can do on your own. I'm just stating the graph form. And clearly these functions will oscillate towards origin. So when oscillate as x tends to 0, this particular thing will go towards infinity. So cos will oscillate between -1 and 1. This also oscillate towards -1 and 1. Okay, so I can clearly see that as x tends to 0, this particular thing will oscillate between -infinity to +infinity. Sorry, this particular thing will oscillate and this particular thing will also oscillate. So if you just make a graph of it, if you just try to find the graph of it, you'll find that this will be an oscillating graph. So in the neighborhood of 0, 0, the function is derivative is less than 0 and derivative also greater than 0. So you cannot state that in the neighborhood of 0, 0, your function is increasing or decreasing. So therefore, this serves as a purpose. Okay, so this is a counter example which suggests that f dash x naught is greater than 0, but I cannot say that function fx is increasing or decreasing. Why? Because as you can clearly see, if f of x will take the values from x minus x square to x plus x square. So clearly you can see that your amplitude, since sine of 1 upon x square is sine of 1 upon x square, that will be -1 and 1. So therefore, this will oscillate between x minus x square to x plus x square. And in the neighborhood of 0, 0, you can clearly see that this particular function can be the graph of this particular function, as you can clearly see, that this will oscillate, and since it will oscillate, so I cannot say whether this is your f dash x. This is your f dash x versus x. So about this particular thing, so I cannot say f dash x is positive or negative because it is going up and down and up and down. This will oscillate, and since it will oscillate, I can really state that in the neighborhood I cannot have any clue whether the function is increasing or whether the function is decreasing. So with all certainty, I cannot say that whenever f dash x naught is greater than 0, it implies f is increasing in some neighborhood of x naught. Again, let me do this for you. See, if f dash x naught is greater than 0, let me take the example x plus x square sine of 1 over x square. So if I see f dash 0, what will I get? I'll get x plus x square sine of 1 over x square. And if I take this divided by x, what I'll get simply 1. So f dash 0 is equal to 1, and certainly it is positive. But in the neighborhood of 0, function is increasing. This is true or false? The answer is not true. Why? Because in the neighborhood of 0, as you can clearly see, this particular thing will blow up, and this particular thing will lie between -1 and +1. So since it will lie between -1 and +1, so x minus x square, it will oscillate between x minus x square to x plus x square, and so this will be again an oscillating graph close towards 0. So this will be an oscillating graph in the neighborhood of 0, 0, and therefore I can clearly say that a function is not increasing. So here, in the neighborhood of 0, 0, you'll find that a function is oscillating, and since function is oscillating, it will come up, it will come down, it will come up, it will come down. Since it is a smooth function, so I can clearly say that your derivative will change the sign, or in other words, I can say your function will appear to be increasing at some interval and decreasing at some particular interval. So if you need a further explanation to this, I can have a graphical, more graphical kind of representation. But for now, I can clearly state that for this particular thing, just know this particular counter example. It will be very important for your interview purposes also. So I hope I have been able to deliver you the idea. See, again, if you're getting the, you just see that if you just magnify this particular thing, because in the neighborhood of 0, 0, how to explain it further? In the neighborhood of origin, what you'll find that your function is oscillating, and since your function is oscillating, so in the neighborhood of 0, 0, it will take this kind of shape, right? So it will take this kind of shape. When it takes this kind of shape, so it implies that the function is dipping and again increasing, decreasing, this kind of so positive. So this is a kind of thing. So it will oscillate, and since it will oscillate, I cannot have a clear idea as to whether your function is increasing or decreasing. So in any neighborhood of 0, you will find that your function is oscillating, because as x tends to 0, this will oscillate. So now we'll print minus 1 plus 1. So this is a kind of sketchy idea that I'm giving you. For more further thing, we need to take sequences, and that we can take if you insist. Okay. I hope this was it. Another question that I think to look on is, I think it is an easy question that was asked in the examination. And I think we should take that also in consideration. So this was about two variable calculus. This particular question was of multi-variable calculus, and then the question was regarding the continuous extension. That particular question was regarding the continuous extension of the function. So let us do that particular problem also. So question that was asked, this is question number 23. So question number 23. We are doing question number 23. Okay, so let us do question number 23. So question number 23 is regarding this particular question. So f is defined from D to f is defined from D to R, where D is a subset of R square, such that what does it contain? So D contains x and y belongs to R square, except x comma 0 belongs to R square. So D contains, D is given to be equals to R square except x comma 0 belongs to R square. So what has been not there? So your x axis is missing. So your x axis is x comma 0. So this is y equal to 0. So y equal to 0 is this. So what they have excluded, so this axis they have excluded from the domain. Okay, so this is, they have excluded this from the domain. Now what has been asked, what is continuous extension in general terms? So for example, your fx was given to be, just giving you an idea, I'm not getting query. So if x is not equal to 0, can it be continuously extended? Yes, it can be continuously extended by extending the definition of function at x equal to 0, 0. So this is how you can continuously extend a function. So initially at x equal to 0, your limit is equal to 1. So what I have done, but at x equal to 0, your function is not defined. So I have continuously extended, or I have defined the function at x equal to 0 to be equal to 1. Okay. Note that this particular definition should be unique. This particular definition should be unique, obviously. Yes. So about this particular question. So first thing that has been asked, that f is discontinuous or real or not. So fxy is equal to x into sine of 1 over y. So this is the question where pi should not be equal to 0. See, pi is equal to 0 as given. So can it be read? So what about this particular function? This function is continuous. This fx is continuous on D, because on D your function is well defined, because where y is not defined, it is only not defined at y is equal to 0. So what I can do, that function is continuous on D by algebra of continuous functions. So by algebra of continuous functions, since x is a continuous function, sine 1 over y, wherever y is not equal to 0 is a continuous function. So algebra of continuous function, fxy is continuous on D. There is no problem about it. So what is problem? Can it be continuously extended or not? Yes, it can be. See, if I have to extend it, so I'm writing f0 comma 0 is 0. So I'm stating that your function will be 0 at origin. So now let us see fxy. So I'm just taking the modulus of it. So fxy I'm written as modulus of sine 1 over y, and sine 1 over y will be less than equal to 1. So this will be less than equal to modulus of x, and modulus of x can be made less than epsilon whenever your x and y are approaching towards 0. So it clearly implies that limit fxy whenever x and y tends to 0 comma 0 is simply 0, and it is equal to f0 comma 0. So your given function can be continuously extended towards origin, can be continuously extended to origin by putting f0 is equal to 0. So therefore f can be continuously extended continuously extended over the domain D union 0, 0. So over domain D union 0, 0, your extension can be made by redefining the function at 0, 0 by 0. Now what about R square? So in R square, what will be the term? Let me tell you. So in R square, consider x is equals to say a, and for simplicity I'm just taking a to be non-zero, arbitrary real number. Let's say x is equal to a, and a is a non-zero arbitrary real number. Because a equal to 0, if I take, then I'll get into some specific cases of the above, which I've already discussed. So I just don't want to follow your trial, I just want to contradict the fact that your function cannot be continuously extended over R square. So just I need an example, so therefore I'm putting an example. If you have certain other things in your mind, then do tell me on your comment section. Okay? So if consider x equals to a, and a is a non-zero real number, arbitrarily defined, then consider a, 1 over n pi, and consider a, 1 over 2n plus 1 pi by 2. So clearly both of these, as n tends to infinity, converge towards a, 0, and this also converges towards a, 0. So in R square, you have also this y equal to 0. So, and since at y equal to 0 function is not defined, so you have to define something at y equal to 0, right? So you have to define something at y equal to 0. So what about f a, 0? What should I define a function at a, 0 in order that function gets continuously extended? Okay. So let me just check the limit of it. So this also 1 over n pi converges towards a, 0, and a, 1 upon 2n plus 1 pi by 2 also converges towards a, 0. So both of them are converging towards a, 0, and your given function is non-zero, is a continuous function whenever y is non-zero. So for all y non-zero, your function fxy is equal to x into sine of 1 over y is a continuous function. So if I impose f n pi, so I will get what? I will converge towards f of a, 0, and similarly f of a, 1 upon. If in case I want to extend, then I need to do what? I need to use this limiting definition. I need to use this limiting definition as the value at a, 0. So I need to precisely and uniquely define f of a, 0 in order to continuously extend function over a, 0, because at y equal to 0 function is not defined. So let me take the limiting value at a, 0 and put that limiting value as value of the function at a, 0. In case I am able to do it, then I can simply say that function can be continuously extended to point a, points a, 0. So let us see if it happens or not. So as n tends to infinity, f of a, 1 upon n pi will converge towards what? This will converge towards 0. Since you can clearly see a into sine 1 over y. So I am writing this particular function so that you can keep a mark on it. So f of x y is given to be x into sine 1 over y. So you can clearly see that if I am putting 1 over n pi here, so this will go towards 0. And what about this? This will go towards either plus 1, plus a, or minus a. So I cannot uniquely assign a value to f a, 0. Therefore, f cannot be continuously extended to a, 0. And a, 0 certainly belongs to R square, which implies f cannot be continuously extended on whole of R square. So I hope this is clear to you, and by this I'm summing up the lecture for today. We shall meet tomorrow again with a few more questions. Till then, take care. Bye.